Hello, this is video 51. We just talked about elastic collisions in the previous video where we said kinetic energy was conserved. So you can imagine in this video, with inelastic collisions, kinetic energy will not be conserved. So this is just the second case and the only other case of collisions that we're going to be discussing. So for inelastic collisions, momentum is still conserved. So as I've said several times, momentum is conserved for all collisions, all explosions. But kinetic energy is not conserved in this case. So this type of collision is more realistic. As I mentioned in the previous video, when two objects collide, they're going to warm up a little bit, there's going to be friction, it's going to make sound. That energy will be transformed to another form. The kinetic energy will not be conserved. So this is more realistic, and all collisions that we do in this class will be inelastic unless the problem explicitly says that it's not, or that it's pool or billiards. For that we said it would be elastic. Anything else is going to be inelastic. Now within inelastic collisions, there is a special type of collision called the perfectly inelastic collisions. That's the special type where the objects stick together. That's what this picture is showing right here, where the objects are colliding and then sticking together. So if that's the case, that's perfectly inelastic. But for just plain inelastic, they do not have to stick together. Doesn't matter. So if they do stick together, then it simplifies our equation a little bit. This is still conservation of momentum. The same exact equation as above here. The only difference is that if they stick together, then the final velocity of both of them is the same. So instead of writing v1f and v2f, we can factor it out and just call it vf. Now if you have an explosion, you can write a similar equation, an explosion like we did with the cannonball example, where the two objects are together and then they're coming apart. In that case, you can write m1 plus m2. They both have the same initial velocity because they're stuck together, and then they can come apart, so you have m1 v1 final plus m2 v2 final. So that's just the opposite of this one. So the second one here is more for an explosion, and the first one here is when they stick together after the collision. But it's just rewriting conservation of momentum. So let's take a look at it your turn, and then we'll do one example. A small car and a large truck have a head-on collision, which has a larger magnitude change in momentum. So the reason I have this in this section here is because this is an inelastic collision, because we know that there's definitely going to be some energy transformed to heat and noise with all that destruction, that you're definitely going to have energy lost to the surroundings. So it's not going to be conserved. And so how do we figure this out? Well, it's about understanding conservation of momentum. Conservation of momentum says that your momentum doesn't change from the initial to the final. So I use the letter P for momentum. So P1i, I'm just writing P so I don't have to write m1 v1 initial, plus P2i, right? The initial momentum equals the final momentum. So this is just the same thing as writing m1 v1 initial plus m2 v2 initial, etc. So if we rearrange conservation of momentum and put all the objects number 1 on one side, we have P1 initial minus P1 final. Then on the other side we have P2 final minus P2 initial. Well, look what we have here. Final minus initial is a change. That is delta P2. Now P initial minus final is the negative of a change. Right? It's negative delta P1. So you can see that I'm asking for the magnitude change in momentum because I want us to disregard the negative sign. If we disregard the negative sign, take an absolute value, they have the same change in momentum. And that makes sense because if one object increases its momentum, so let's say the car ends up rebounding maybe faster than the truck, it's increasing its momentum, well then that means that the truck has to lose momentum so that the total momentum is conserved. So let's do an example. We have a 700 kilogram car with an initial velocity of 20 meters east, rear ends a truck, stop for red lights. The two vehicles interlock as a result, so they're sticking together, so it's inelastic for sure. It's actually perfectly inelastic. Find the velocity of the wreckage. So for all collisions, I write down the givens. I'll have M1 be the car, 700 kilograms, M2 be the truck, 900 kilograms. V1 initial is 20 meters. It's east, I'll call that positive. The truck, V2 initial, is stopped for a red light. That's 0. And then we have V1 final. Well, they stick together, so we just have V final because they both have the same final velocity. So because this is perfectly inelastic, we can now write down the equation M1 V1 initial plus M2 V2 initial equals M1 plus M2, all of that in parentheses, times V final. They stick together. Alright. Having trouble with my little f here. There we go. So to find Vf, we just divide by M1 plus M2. So Vf equals M1 V1 initial plus M2 V2 initial over M1 plus M2. And now we can plug everything in, and I'll let you plug the numbers in. They're right here. The V1 initial, the V2 initial is actually 0. I usually would actually have crossed it out right there. And so we're just going to plug in 700 times 20 divided by 700 plus 900. And that's going to give us 8.75 meters per second as our final velocity. And this is a one-dimensional collision, so it's going to be to the east like everything else. And that was part A. Let's do part B of this example. Part B says, what are the initial and final kinetic energies? So this is an inelastic collision. So can you, before we do the math, can you tell me, or can you tell to yourself, are those energies going to be the same, the initial and the final energies? So let's take a look. So the initial kinetic energy just means 1/2 M1 V1 initial squared plus 1/2 M2 V2 initial squared. It's just the initial kinetic energy of each. And the truck was at rest, it did not have any kinetic energy. So we're just plugging in 1/2 M1 V1 initial squared. So we're going to plug in 1/2 times 700 times 20 squared. And that gives us 1.4 times 10 to the 5 joules. Now let's take a look at the final kinetic energy. So this was KE initial. Now let's look at KE final. It's going to be the sum of the final kinetic energies, but since they stick together, we can just pretend that they're one object that has the mass of both objects. So we can write it like this. 1/2 M1 plus M2 in parentheses, just one object that has the mass of the car and the truck, times the speed squared. So we plug in 1/2 times 700 plus 900, and then times 8.75 squared, that's the Vf that we just found in part A, and that gives us 6.1 times 10 to the 4th joule. So I paused there just in case you're thinking it was going to be 10 to the 5. So you can see that the final kinetic energy is less. KEF is less than KE initial. Does that make sense? Yes, it does, because we said in inelastic collisions that kinetic energy is not conserved. It's going to be converted to some other form. That's why you don't have as much kinetic energy at the end than you did at the beginning. So just to recap, our collisions, elastic collisions, inelastic collisions, momentum is conserved in both types, but the difference is that kinetic energy is not conserved in your inelastic collisions.